Hey everyone, this is joint work with Ziyang, Chen, and Owens. Let's consider the sound you might hear in this scene. The sounds you hear are the real sounds from one of our apartments. Apparently, we paired it with a much nicer picture here. At first, you might think there's not so much information in the ambient sounds, and you might describe the scene as silent. But if I move around the room, the sounds will change. For example, if I move closer to a refrigerator, this is the sound we hear. And when we go near this vent, we can hear this sound. When we move over here to the window, the sound changes again. Even words can change the sound we hear. The effect is kind of like putting a seashell in our ears. Actually, humans can use these subtle cues in ambient sounds to understand scene structure. For example, if we hear the car or wind sounds outside, it's probably because we are standing near the window. And we can easily tell whether we are in a subway station from the reverberation. When the sound struck a surface, it leads to echoes, and the echo will cause some interference patterns. Objects can also change the sound field by casting a sound shadow. If we have this multimodal data, we can learn the correspondences between images, depths, and ambient sounds. If we could learn these correspondences, there would be a lot of things we could do. Paired images and ambient sounds could provide a natural signal for self-supervised multimodal learning. Beyond that, sounds could simply provide additional features for multimodal systems. And sounds could also be helpful when a robot's other senses fail, as a kind of backup modality. For example, when the lights in the room are turned off, a lens is occluded, or a camera fails. It's worth noting that these cues are quite different from echolocation. In echolocation, the robot has to actively emit a sound with a speaker. Some other works try to understand the scene using sound landmarks. These methods largely use distinctive and loud sound sources, like ringing phones or alarm clock. But it's unclear how often these sounds appear in the real scenes, or whether the sound propagation model is a good one for the real world. And where there has been a lot of work that use audio and video data for self-supervised learning, it hasn't considered these very quiet indoor sounds. Inspired by this, we wanted to see if ambient sound could be used to estimate 3D scene structure in real scenes. So we collected a data set. We walked around the campus and collected paired audio and RGB data. We call this the Quiet Campus dataset. It contains about 46 rooms and many hallways from 12 different buildings, about 14 hours in total. Here are some samples from the dataset. After collecting the data, we want to see whether we could estimate distance from the wall. This is what we did. We tried to regress the distance to the wall using this standard network called VGGH. In the paper, we formulate this regression problem in several different ways. Here, we just show one of them that formulate it as a classification task, and we let the network to decide whether the recorded audio is near or far from the word. We defined the near as within half a meter. We also considered a relative depth estimation task. Given two audio clips, the model needs to distinguish which one is recorded closer to the word. For both of these two tasks, our audio model performs well above Chen's, and as you might expect, you can solve this task much better if you use images instead, but it's still pretty good. Here's a demo that uses the Chen model to evaluate on an unheard room. As we move closer or further from the word, the predicted probability of being near to the word changes accordingly. We divide this room into 5 by 5 grades and average the score of all audio samples in every grade. It shows that the model can distinguish the boundary of the room very well. We also propose a self-supervised learning method for RGB images and ambient sounds. We let the network to guess whether a pair of RGB images and a pair of audio have the same order. The model solves this task by learning depth information for both modalities, and this will benefit the downstream task. We use the feature we learned from the previous model and then train the learner model to solve the relative depth order task. The comparison here shows that the model is effective on depth-related tasks. We run the robot to navigate along the wall using the ambient sounds on different tracks. Here's a demo video of the robot running on different tracks. The controller of the robot is very simple here. It's just a P controller that drives the robot closer or further from the word according to the prediction. To avoid introducing any other sound sources, the robot will stop and listen to the ambient sounds from both left and right side. The robot starts from a random location with a random orientation, but it can still correct itself when navigating along the word. In one of these rooms, we compare the model using ambient sounds with the one using RGB images. For simplicity, we use very similar controller and data for audio and video model. We could of course get much better results here if using more advanced video algorithms. The quantitative results show that the model using ambient sounds perform pretty well on doing this kind of task. In this work, we found that ambient sounds convey a surprising amount of information about scene structure. To investigate this, we collected a quad canvas dataset and used ambient sounds for self-supervised multimodal learning as well as estimating distance to the world. Thank you.